Hi, this is Michelle Cullen, and this is a quick background to get you started for the background of Planet Designer Lab. I have a longer tutorial that will go through much more of the science if you're not familiar with some of the. Learn how different parameters of your planet that you're going to design could affect the ability to have liquid water as you know it. And we have these terrestrial planets that have only one of them that we know of has liquid water. There are other worlds and moons that have liquid water farther away, but they are underneath deep, vast layers of ice. So when we are filling out our chart in the lab, we're going to use a simple term of different measuring sticks. One of them is the astronomical unit you're familiar with, so you can figure out how far your planet is from the sun in terms of the Earth-Sun distance. So we'll just fill that out in this table, which will be table 1, and you're going to look up the different planets and look up their AUs from the sun. Then you're going to figure out their average temperature, and I've given you some different resources. One simple resource is the NASA website, which has the temperatures right here and has a thermometer that you can use to guesstimate the approximate temperature. There's also a chart on your lab that gives you a range of temperatures below, so don't forget to look at this. You can look at the range of temperature on Mercury, which goes from very hot to very cold because it has such a slow rotation, and it can get extremely cold on the side away from the sun. You'll look at the other temperatures and just sort of do your best to figure those out. Another great website to help you on this is called the 9 Planets, and it has all the planets. You click on planet, which is on the top, and you can pick the different ones. You can pick Venus, and you can go down, and it has some quick facts that will give you the surface temperature and also astronomical unit. So if you're not familiar with Kelvin and that it's a unit absolute scale that's 273.15. It turns out that space is 2.7 Kelvin, which is minus 270 around. So it's pretty cold out there, but it's not empty. There's still a little bit of heat in space. If you want more detail, look at the other video. Then you're going to figure out a size of the planet, and this really isn't a super big deal, but in reality it is. And more massive planets will have more gravity, so you're going to look at that in OpenStack's astronomy book, and you can look on Appendix F, and there's charts, and you can look at the mass in terms of Earth mass for the different planets. And also there's the dwarf planets in there too, and you can look at the surface gravity. It does not have the moon on here, but you can look over here. The moon is 0.012 Earth mass, and you could look up this gravity in terms of G. You could just Google that if you want. Habitability, you can read this wonderful article. It's a little complicated, but I love Fraser Cain's Universe Today. It talks about how planet size could affect your habitability, and also how it could have an atmosphere. Now think about it. If you're small and you don't have a lot of gravity, how could that affect your atmosphere? How do the smaller planets and worlds have atmospheres? How about the larger planets we are going to study next week? They have massive atmospheres. Albedo is a new term we're introducing in this week, and albedo is simply reflectivity, and so you're going to be programming in the bond albedo, which is another term. Normally albedo is like a number like 0.5 for sea ice to 0.7. regular fresh snow could be all the way up to 0.9. That means it has a high reflectivity, has a high albedo. And the bond albedo, you just turn that into a number like a percent without the percentage. So the fresh snow albedo could be 90 bond albedo. So if you if you designed a planet that was all white, full of fresh snow, you could put in your albedo as 90. If it was a dark one, you could put it in as a number that's much lower, like 10 or 20 or 30. So if it was a specific color, there's actually apps that can convert and tell you what color, like if you had, a fluorescent pink planet, it could tell you what the albedo was of that. But in terms of Earth, we get average albedo. And that's what your average planet is. So you can compare and just look here at the average albedo of some places on the solar system. And it's surprising that the moon is so non-reflective. It's so low. It's only 14 on the scale of 1 to 100. And just imagine if the moon was actually made out of not like dark regolith, dark rock. It had a very light white kind of bright sand, how that would make it brighter on the Earth. Okay, moving along, we're going to look at greenhouse effect, and this is very important. So just the big idea is that planets can have strong or weak or medium greenhouse effects, and strong would be Venus, weak would be Mars, and Earth would be just right. And the greenhouse strength, I just want to quickly go over, is related to the amount of gas that we have. So we have the amount of atmosphere. So thicker atmosphere can have more of a greenhouse effect, and thinner atmospheres have less. So thicker atmospheres have more atmospheric pressure. We turn those in terms of a millibar or bars, and Venus has 93 bars or 93,000 millibars. So there are 93,000 particles per square meter, whereas in Earth, if we had a square meter, we'd only have 1,000 grams per meter squared, which would be 1 bar, and on Mars we only have 3 grams of molecules per meter squared. So the amount of atmosphere is very thin on Mars, and there's very little carbon dioxide, which is a greenhouse gas. And on different planets, we'll have different greenhouse effects. And so basically it's just like in your car or a greenhouse, the visible light comes through, is absorbed into and reflected back as infrared light, which is still light but not visible to us, and that gets reflected off of the greenhouse gases and keeps our planet. The energy balance is important too, and there's just a quick video you can watch, and we want to be just right. So habitable zone is one more concept. What is a habitable or Goldilocks zone? You're going to look that up, and you're going to also learn about how the mass of the star can affect the temperature of the star, and the temperature is obviously going to be affecting your ability to have liquid water and how close you can be to it. So more massive stars than our own, we're in a G-type star right here, and here's Earth. More massive stars are going to put out a lot more energy. So in your program, you're going to put in, is it 1, 2, 50 solar masses? What kind of star do you have? How big is it? How much energy? How hot is it? And then once you've gone through all that basic part, then you're going to go to this program and you're going to design your planet. It's called Planet Temperature Calculator. So this no-frills planet temperature calculator won't fit on my Screencast-O-Matic, but I'm going to show the right side. If you go to the link, it will have a page here with your introduction. You'll go to Build, which is on that right top corner, and then you're going to change the parameters. This first one is called, click on the tabs up on the top. The first one you can't see here is called mass, and you're going to change the mass. Then you're going to change your distance. Maybe it's going to be 2, 3. It's not a, I wonder if you could do 1.5. We'll see if we can do that. The albedo, remember, you can go back to your lab. Earth is about 29, so you can make it more reflective, more white. Change that number, change your greenhouse effect, make it really strong greenhouse. And then, let's see if I can move this around so you can see. There's a summary on the right side, and it will give you a summary of what you did, and then you'll click in your results, and it will tell you that this is above the boiling point water of Earth, so it's too hot. I guess we need to change some things. So then just play around with it until you figure out a planet that can have water that's different from Earth, and see what you can come up with.